community. Recording is in progress, and today's presentations will be clustering of PASC patients using semantic similarity, and this issue of really defining characteristics of post-acute COVID syndrome patients is a very interesting and important issue. So I'm actually really personally very intrigued to see what's going on with that. And Justin, Reese, and Hythem, Sidky will be talking. And then the monthly Recover Long COVID project team updates by Emily and Melissa. Next slide, please. And then next week we have the machine language MLP team update, PASC clustering pipeline and GAP insights with Peter and Justin. May 2nd, practical machine learning for COVID-19 using EHR data, case study using N3C and phenotype 4.0. The week after that, May 9th, is the BARDA challenge updates, and that'll be interesting to see how that's progressing. May 16th, cardiopulmonary testing and addressing issues like fatigue and pediatric PASC. May 23rd, outcomes of COVID-19 in patients with hemophilia, and the monthly Recover Long COVID project team updates. And then the Memorial Day holiday, no presentations. Next slide, please. So remarkably, we seem to have essentially 5 million COVID positive cases. It continues to grow quite rapidly. 72 sites, 13 million patients. This has gotten to be really remarkably large scale. Next slide, please. And so without further ado, Hythem or Justin, whoever goes first, we're looking forward to hearing about clustering of PASC patients.
Great. I'll be going first, and then I'll hand it over to Hythem. Can everybody see my screen? Should say clustering of PASC patients using semantic similarity. Yes. Okay. Yeah. So I'll be talking about our work clustering long COVID patients using semantic similarity, which I'll explain in more depth for those of you who are not familiar with it. But first, I wanted to say this is sort of cross-cutting work and involves a lot of people, and I'll tell you who they are hopefully at the end. But the big idea here is our main goal is to cluster long COVID patients and sort of investigate what subtypes of PASC exist. And obviously clinicians and biologists who've been studying this for a year or more now have some idea what types exist. But the idea here, the big idea, is to do unsupervised learning in machine learning parlance, to let the data tell us what types of PASC exist instead of the other way around, and hopefully gain some insight into the underlying biology of long COVID. And this is, as I said, part of cross-cutting work with the Recover clustering team. That's Reese Brown, Melissa Handel, Peter Robinson, Sean O'Neill, Hythem, who you will hear from in a minute, Hythem, Sidky, and many others who I'm not mentioning here. I'll mention at the end. And also, this is also cross-cutting, I wanted to say briefly, with our MLP subgroup, which is the goal of which is to construct reproducible machine learning workflows in N3C. And so for this and other projects, we've made reusable tooling that we can use for other projects, including a Python library to leverage ontologies and semantic similarity measurements in N3C. And this will be useful, we think, in future projects like the rare disease and COVID-19 work that Melissa Handel and Brian Laraway are leading. We've also made a Python library for making and analyzing clusters using a method called k-means, and actually characterizing those clusters once you've made them, which is in some ways not trivial. And this, as I said, relates to work for the MLP working group. That's Peter Robinson, Johanna Lumba, who work behind the scenes to make a lot of the data that we use to actually sort of fuel the the analysis I'm going to show you, and also the good algorithmic practice group led by David Sonner. There's incidentally, another parallel pipeline, which I won't talk about today, to predict AKI and cardiovascular outcomes in COVID-19 patients, which uses some of the same tooling. Blessy Anthony and others are involved in that. I won't go into great depth in depth here, but there are several parallel clustering efforts going on here. But the idea that is in common with all of them is to make data-driven clusters of long COVID patients. The work I'm going to describe today uses semantic similarity-based clustering, and it uses an algorithm called k-means. That's this talk. Hythem in a minute will tell you about his work on embedding-based clustering using embeddings called SNOMED-DVEC, and he'll explain that in greater depth. And we're also investigating other algorithms such as spectral clustering using the same semantic similarity patient-patient matrix, and also network-based clustering. This is led by Reese Brown, Matlock Brown, and Benjamin Moore, and Hannah Blau is leading the spectral clustering algorithm work stream. So the goal here is to cluster long COVID patients using phenotype data derived from the N3C actual OMOT tables. So we have to make clusters, analyze them for clinical relevance, and we're also interested for several reasons on the generalizability of these clusters. In other words, we make clusters, and how, if we move to a different set of data, different data models, different data partners, how well do these clusters generalize? And I'll show you some data about that. And along the way, we hope to, and I think we already have, provided some reusable code for the N3C community to use. So the first problem is we need to somehow extract and compare phenotype data for all these patients, starting with the N3C OMOT tables. So the clustering requires a measurement of patient-patient similarity. And so we get the patient-patient similarity sort of n by n matrix of all these patients and how they compare to each other. Then we compare the HPO terms. This, which I'll go into in a minute, provides an elegant way of assessing patient-patient similarity using all the HPO terms for long COVID that we have available, and sort of a way that takes into account information content and in a kind of a fine-grained way. And this actually also required operationalizing OMOT to HPO mappings that Tiffany Callahan and Andrew Williams helped make. And these are useful, as I said, for other projects. So this to sort of frame the problem that we are posed with before we make patient-patient similarities. If you consider these two patients, here's patient A, here's patient B, we might have three OMOT phenotypes for this patient: respiratory finding, acute kidney injury, chilblains. In this patient, cough, transient renal failure, clearing throat, hawking, and chilblains. So obviously it's trivial to do exact matching between these. And if you did something like SNOMED rollups or something like that, you might find that respiratory finding has some fuzzy relationship with cough, and acute kidney injury has some relationship to transient renal failure. But there's actually a better way of doing this, and which is the way we've implemented it, which is to calculate the information content of the common ancestor for each pair of terms. So from the top, if you're comparing two phenotypes from two different patients, acute kidney injury and transient renal failure, we map those to HPO using Tiffany and Andrew's mappings. This one maps exactly to acute kidney injury. This one might map to reversible renal failure. We find their common ancestor, which is renal insufficiency, and we calculate the information content of this term. So the information content, conceptually, if you're not familiar with it, is a measure of sort of how meaningful or surprising a match on this term is. And so if a term is very frequent, then the information content will be kind of low and you'll be less surprised. If it's a very rare term, then you'll be more surprised and the information content will be quite high. So what we do, this is an algorithm called phenomizer that was published 10 or more years ago. As far as I know, it's not been operationalized on EHR data up to this point, but we we calculate the patient similarity in the following way. We take the average of the information content for each phenotype in patient A and its best match for patient B. We average those, and then we do the reverse. We find the best match for each phenotype in patient B to patient A. We average those, and then we take the average of the average. And so in some sense, this is sort of an average information content for all the HPO terms between these two patients. And this kind of gives us, as I say, kind of a fine-grained, elegant way of getting a sort of a floating point number for how similar these two patients are. This, by the way, is shared, as I said, as a Python library on N3C. Anybody that wants to use it for any other project is welcome to do so. I can help you do that if anybody's interested, but it's already shared on the enclave, so anybody can use it. Okay, so that gives us patient-patient similarity. So now we can actually do the clustering. So as a first experiment, we found all diagnosed patients from one data partner. That gives us 1,234 patients. So we're just looking at one data partner because we're not touching yet on the idea of generalizability. We extract all of their long COVID HPO terms. So in other words, there's a lot of phenotype information we could use here. We're only clustering on the 287 or so long COVID HPO terms that were shown in Peter Robinson and others' work to be involved in long COVID, or actually to define long COVID. We generate an N by N patient-patient similarity matrix using that library I just said. And then we defined K clusters or centers. This is kind of what K-means does. We sort of randomly pick, if we're clustering on, say, 5 clusters, we pick 5 points in latent space and put the patients in whatever cluster they're closest to. We refine the center based on each of the memberships of each cluster, and then we iterate and just keep doing that until the clusters sort of converge on the 5 or so clusters that we want. This, by the way, is also implemented as a shared Python library in N3C. Anybody can also use this. This is not actually just the clustering, but also a lot of tooling to analyze the clusters, as I said. Okay, so what does the data look like? Here I'm showing you on the left the first 2 principal components of the space under which we're clustering, and I'm coloring these by you'll notice there are 5 different clusters here. That's because we clustered with K of 5. That means we asked for 5 different clusters. And you can see the space under which it's sort of clustering these patients. And so on right, I'm showing you the pairwise similarity of patients by cluster. So in other words, here, I haven't exactly delineated these, but here's cluster 0 against itself. Here's cluster 1, cluster 2, 3, and 4. Sorry, we're starting with cluster 0 because we're computer scientists. And you can see the off diagonals sort of show you how similar each cluster is to other clusters. I'll dive down into that in a minute. Okay, so what we're actually interested in here is to kind of dive down into the biology and see if there is anything interesting about these clusters biologically. And so what we did was you can do a chi-square to find HPO terms that correlate with cluster membership. And so the same HPO terms that we used to cluster the data can also help us define the data using a chi-square test. So we found 49 long COVID HPO terms that correlate with a particular cluster according to chi-squared p, a p-value better than E-6. I'll dive down in a second and tell you what those are. But we also were interested in sort of getting at whether these clusters are generalizable across different data partners. So I'll remind you, the data that I just showed you is just one data partner. So if we do clusters from, say, 4 other data partners put together, again, U09.9 patients, and we cluster them with a K of 5. If we do that same experiment, essentially with several other data partners, we find 57 long COVID HPO terms that correlate with particular clusters. Again, E-6 or better as far as the p-value. And interestingly, 44 of the same 57 long COVID HPO terms are the same ones as we saw back here. And so this is sort of starting to hint that these clusters actually are clustering according to some meaningful biology. So what exactly are these clusters? I don't expect you to actually read any of these HPO terms on the left, but what I'm showing you here is each column is a cluster. You'll notice there's 5 columns, and I've sort of color-coded them according to higher level groups of HPO terms. So here, for example, in dark blue are cardiovascular HPO terms that define long COVID. This purplish color is pain. GI. Lab is kind of a weird one because the labs sort of implied different biology, but they're sort of grouped together here. This blue type color here is neuropsychiatric and pulmonary. So this kind of gives us an idea of like what sort of patients are in each of these clusters. And you can see there is definitely some interesting structure here with respect to the biology. The first thing to notice, though, is that you do not want to be in cluster 0 if you have long COVID. These are the most severe. We're seeing a wide variety of symptoms, including cardiovascular, pain, lots of abnormal lab values, neuropsychiatric complications, and pulmonary symptoms. Cluster 1 seems to be similar, only less so. Cluster 2, we're seeing frequent neuropsychiatric complications. Cluster 3, it seems to be sort of a pain cluster and possibly some cardiovascular too. And cluster 4 seems to be defined mostly by pulmonary symptoms. Okay, so next steps here, and we have some data which I just came out today, and I hadn't had time to update the slides. The next steps here anyway are to determine the optimal number of clusters. I sort of picked 5 arbitrarily because that's sort of what others have observed, that that is probably around the right number of clusters, but there is actually a more rigorous way of defining that. Using something called the elbow method, which I won't go into. And then this is also one of the main interesting questions we want to get at, is that how do these clusters generalize across data partners? I mean, I think I've shown you a little bit of data that they generalize fairly well, but a more rigorous algorithm is defined here. So we get U09.9 patients from new partners we haven't seen before. So sorry, we cluster using one set of data, and then we get new patients from data partners we haven't seen before. We measure their similarity to existing clusters using the phenomizer algorithm that I showed you before. And then we measure their similarity to random clusters. So the same patients that we clustered before, only with sort of random cluster assignments. And so good generalizability should show us a strong tendency of patients to be similar to one cluster. In other words, the cluster, each new patient we see tends to want to belong to one of the clusters that we defined previously from a different data partner. And preliminarily, the z-scores we see from this null model, and so sort of conceptually how well the new patients belong to a cluster is very, very large, and the clustering is much, much better than what we would see by chance. And so it looks to us like the clusters we are seeing are fairly generalizable, at least in the experiment where we're looking at 4 different data partners that we have not seen before. And I'll just mention briefly also a generalizable model might be clinically useful. For example, it might alert clinicians of other complications that are common in this cluster. You see a patient, they belong in cluster 0, and the clinician is looking out for a bunch of different complications, but didn't look for example, cardiovascular complications that are very common in this cluster. So it might be clinically useful for that reason. And also, we're very interested in comparing the results I'm showing here with other clustering algorithms. For example, the clustering algorithms Hythem will talk about now, and spectral clustering, hierarchical methods, and so on. I just wanted to briefly acknowledge all the people that helped out with this. This definitely wasn't just me doing this work. The Just Add Coffee hackathons are pretty well attended, and these people tend to show up every day-ish. And also the NLP working group and other colleagues who I've shown on the right here. And I think with that, I will hand it over to Hythem, and he will tell you about his clustering work to do with Snowbed Tvec.
All right, can you all see my screen?
Yep.
Great, thank you. Yeah, so I wanted to pick up where Justin left off. And so this is work we've been doing in parallel to really investigate the same question of, clustering on these long COVID patients. And I won't go into too much of the background because Justin did cover that, but I want to kind of repeat a little bit of the same motivation Justin talked about, but take it in a slightly different direction. So, ultimately what we're interested in, or one thing we could be interested in, is that we want to efficiently represent discrete high dimensional medical concepts. And so here I just have a simple example of 3 patients and 3 conditions: pneumonia, bronchitis, and obesity. And if we were to represent these conditions or concepts in general as separate categories discretely, we wouldn't be able to capture the fact that pneumonia and bronchitis are more similarly related than, say, bronchitis and obesity or pneumonia and obesity. And so, to frame this in a sort of a mathematical task, what we're interested in is we want to take an n-dimensional vector, a very high-dimensional sparse vector that consists of different categories. So we're encoding a number of discrete things, and we want to convert that into a much lower dimensional dense vector that also encodes the information more efficiently about medical concepts. And then then in that space in which these vectors live, we can do arithmetic, basically. So we can compare distances between vectors, and we can say, hey, look, bronchitis and pneumonia are much closer together than bronchitis and obesity, and so on. And there are many different ways of accomplishing this, and this is known as representation learning. And so, whereas Justin talked about leveraging HPO, here I want to talk about SNOMED CT. So in OMOP, we have a mapping to SNOMED codes for conditions of interest, and SNOMED covers a lot more than just diagnoses or medical conditions. This is like a subset of UMLS here. So we have chem, we have anatomy, we have procedures, we have disorders, and their relationships. So you can think of each diagnosis or each procedure as a node in a graph, and then we have edges that relate these different nodes together, and the nodes can belong to different classes as well. So what we decided to do is to leverage prior work that's been done on the SNOMED CT knowledge graph. So a particular group, out of PNNL and Stanford, what they did is they looked at a number of different algorithms that are able to take graphs and convert them into those dense vectors. And I'll kind of save you all like a long discussion, but of the different approaches that they investigated, the one that we settled on was Node-to-Vec, which is one of the ones that they looked at. And Node-to-Vec, essentially, it learns those continuous feature representations from nodes on a graph. So, and then so that they've actually done a lot of the heavy lifting. So they actually took this SNOMED CT, the subset of it, and then they used this Node-to-Vec algorithm to generate vectors. And then what they did is they published the dense vectors along with each SNOMED CT code corresponding to those vectors. And so that is the starting point for the work that we did. Now, once we have a vector, this dense vector for each condition for a patient, there's another task that has to happen. So if I have a vector for, cough and dyspnea and malaise and things like that, I need to be able to characterize a patient based on the different conditions that a patient has. And there are a number of different approaches for doing that, for taking all these different conditions and converting them into a patient level representation. And one approach is to basically generate a weighted average. And the weighted average here is, so each condition in the condition matrix is weighted inversely proportional to the frequency of occurrence. And what that means is we essentially are putting more weight or emphasizing rare conditions and de-emphasizing very common things. And we're actually going to see that in a little bit. So there are common conditions that are, let's say, very non-descriptive about long COVID patients, and therefore we don't want to give them as much weight in our analysis. So once we have patient level embeddings for patients, we actually want to think about a patient's trajectory. So think longitudinally. So I took this figure from the early long COVID work that Emily Pfaff and others have done. And here they described, or they defined, a lookback period. So the period characterizing a patient prior to their COVID-19 diagnosis. And then there's a acute COVID period that we're ignoring. So it's like a blackout period. And then that's for 90 days. And then afterwards, there's a look ahead period. So what's happening in the future. So the post-acute phase. And thinking about characterizing a patient during the look back period and a patient during the look ahead period. So effectively, what if we treat a single patient as if they were two separate patients? There was that patient prior to their COVID-19 infection, and there was that patient after their acute COVID-19 infection phase. So given those two periods and looking at patients both in the look ahead period and the look back period, what we can do is we can take the patient level embeddings for each patient, and then we can generate a representation, a low dimensional representation of those embeddings. What I failed to mention was those SNOMED-DVEC embeddings were 200 dimensional, so kind of hard to visualize. And so what we've done here is we've actually used UMAP, which is a popular dimensionality reduction algorithm, to generate this particular projection over here. And so what are we looking at and what are we looking for? So we're looking at the embeddings where the red dots represent the look ahead period and the blue dots represent the look back period. So each patient has two dots on this figure, but we're also looking for structure. So is there anything that is heterogeneous about the presentation of these data that can perhaps give us insight into potentially distinct subphenotypes of long COVID patients? Now, what we do see is we do see a bunch of isolated points or tiny clusters at the fringes of this large mass in the center, but the large mass itself is more or less fairly homogeneous. And what we're not seeing, to phrase it sort of the negative, what we're not seeing is all of the look back period patients on the left-hand side and the look ahead period patients on the right-hand side. So there's no clear, distinct, separate, like linear separation between the two time periods and their corresponding embeddings. But what there is what we can look at, though, is we can look at how have patients changed as a function of the pre and post-acute periods. Now, this figure looks like a giant mess, and it's not intended to be very interpretable. But what this is just an arrow that's drawn from a patient's before state to a patient's after state. And what we're looking for here is we're looking for, in the dynamical systems sense, an attractor or a set of attractors. Are there specific points or areas in this figure that attracts a lot of patients, so that patients migrate to beginning to end? And we do see, again, some of these isolated islands are attractors for a bunch of patients, but then there's a lot going on here in the center that we can't really see to our eye very easily. And so what we can do is say, well, what if we try to cluster and characterize the perturbation vectors? So perhaps when you add a condition to a specific patient, that perturbs their location just a little bit from where they started. Because after all, a patient representation is a weighted average of all diagnoses, all conditions that have gone into a particular patient in the pre-period and in the post-period. All right, so doing that, now there's a lot here. If we look at the left-hand side, this is the embedding and clustering of the perturbation vectors for the patients. And here we actually see a lot more structure emerging. So we can see it, at least sort of a separation between the top half and the bottom half of the figure. And we see some more, I guess you can say, higher resolution grouping that appears in the figure. And what we've done here is we've just used HDB scan to cluster, to assign cluster IDs to the different groups that appear here. And what I've done on the right-hand side here is I've selected clusters 1 and 2 just for illustrative purposes and identified, because now we're talking about perturbations. So things that patients are losing and things that they're gaining in terms of conditions. Now, this cluster 0 was too small to incorporate because the counts were too low, but this is, again, illustrative. So if we look at cluster 1, so this orange cluster right here, and we look at the conditions that are lost. So the patients, 47 patients lost low back pain, abdominal pain, headache, neck pain, chronic pain. So different conditions that relate to more or less chronic pain. And what they've gained is dyspnea, sequelae of infectious disease, hypoxemia, acute hypoxemic respiratory failure, and tachycardia, among others. So things related to respiratory illness in the post-acute phase. Whereas with cluster 2, for example, we have about 1,000 patients here. They started off with acute upper respiratory infection, cough, but then some behavioral health diagnoses, so major depression, insomnia, anxiety disorder. And what they've gained, again, so talking about those frequent conditions like dyspnea and sequelae of infectious disease, which are not necessarily informative, but we also have malaise, chronic pain, and fatigue, which are distinctly absent from cluster 1. So what we begin to see here, and I'm being impressionistic on purpose, is we begin to see potentially distinct patient phenotypes in the pre-phase and in the post-phase, with a different presentation of conditions that are gained that are distinct between the different clusters. Now, this is all fairly preliminary work, so we are working with that same UO 9.9 group that Justin talked about, but there's a lot of work that remains to be done. So number one, Justin did talk about characterizing the clusters using statistical methods. So that's something we haven't done on these clusters yet, and that's something we plan on doing. And also sensitivity analysis and establishing the robustness of these clusters. What happens under cross-validation, different data partners, and so on and so forth. And of course, because we're dealing with a SNOMED CT knowledge graph, we can also incorporate embeddings of drugs and procedures. We're not limited to conditions alone. And then, here we did a very coarse longitudinal analysis looking at patients in the pre-phase and the post-acute phase. But in reality, we can slice up a patient's trajectory as fine, well, not as fine as we want, but we can definitely go for higher resolution. And that means we can start thinking about clustering patients based on their trajectory, not just based on their endpoints, but the actual trajectory of how their conditions have changed through time and what kind of interventions they experienced. And finally, the SNOMED CT graph leverages the actual nodes and edges that have been encoded by subject matter experts in the in that specific knowledge graph. But there is other important information that can be used, which relates to the co-occurrence information as far as when and how diagnoses and conditions are present along the patient's journey. And that information is valuable, and it can be incorporated to essentially generate or improve the quality of the embeddings for both the diagnoses and, as a result, for the patients. And so with that, I guess I'll stop here and, I guess take questions, or we can move on and take questions at the very end. Thank you.
Let's have a little bit of this discussion now. Any questions? So I have a couple. It's really fascinating work. And so one obvious question, at least in my mind, is the question of the relationship between what you get when you map to HPO versus what you get when you analyze SNOMED to VEC, because they seem like very complementary methods, but presumably there ought to be some concordance. And I think you've alluded to that obliquely, but I'm sure you've given that a lot of thought.
Yeah, so I guess I can share a little bit, and Justin, if you want to add to it, that'd be great. So, the way if the phenomizer algorithm. So I'm not terribly familiar with HPO and the mapping between them. So there could be, I guess bijective mappings that go on, which might muddle things a little bit when you look from SNOMED across to HPO. But another thing that is important to think about is the algorithms themselves. So the embeddings that we're getting that have been learned off the knowledge graph function distinctly differently from what we get from the phenomizer algorithm. And I think Justin can definitely talk about that a little bit more. So the objectives might be a little bit different that govern the generation of these embeddings. And as a result, the results can be a little bit different. That doesn't mean they're mutually exclusive. So one can learn something from one method that you can't really infer from another method. To put it differently, even when looking at the embeddings that are gained from SNOMED to VEC, some are particularly good at representing concept similarity, which is what I chose, the node to VEC result. Others, like Poincaré embeddings, are much better at characterizing dependencies, temporal dependencies between different conditions, right? So you wouldn't say, well, why doesn't this result give us something the same as this one? You would basically evaluate each one on their own merits and their own terms and say, what can we learn from both of them? And then Justin, I don't know if you want to add something to that.
Yeah, I guess in some sense, the first thing to say is we're definitely interested in seeing also how our clusters comport with Hythem's and the other algorithms I mentioned. But in some sense, Hythem is doing something a bit more sophisticated, which is to include patient trajectory in the whole thing. So you wouldn't be surprised if the the clusters that he derived from doing that would be, I mean, the biology of what he's getting at is slightly different. And so you wouldn't be surprised if they didn't completely comport. But saying that, you wouldn't also be surprised if you saw some of the same sort of biology emerge in some of those clusters. So I think we just kind of have to do our best at characterizing them with statistics and then just see how they comport. My vague sense is that spectral clustering on the semantic similarity matrix, as I said before, and then the Reese is doing some other algorithms, might comport a little bit better than how our clusters comport with Hythem's. But I'm very, I think what Hythem's doing is really great. I think it's a really.
Oh yeah, no, don't get me wrong. I think they're clearly complementary. I mean, if you use a single method, you don't necessarily have anything very good to cross-check it with. So I think that they're different views of the same thing, and it seems to me that some of the differences and similarities would be very, very enlightening. Okay, so I have other questions, but I don't want to hog this. So let's see. Can you clarify what you refer to as missingness? Is
Yeah, so that was me just responding to a question from Fadl Al-Akwad. So yeah, he asked about missingness. So, at least looking at the conditions, we don't really have missingness as such. So if you want to think about, missingness in the sense that what if a patient has a certain condition that isn't present in their EHR, that's a level of missingness that we're not really handling here. However, at least, the data set that we're working with, at least that myself and Andrew are working with, is after a lot of filtering work that's been done by Emily and others around ensuring that there's EHR continuity and sufficient baseline medical history for patients. As for condition loss and gain, I'm sorry, I should have elaborated it. So a loss is essentially a condition that was present pre-COVID-19 that was not present in the post-acute phase. And then gain is a condition that was not present before but was present after.
So do you have a estimate? And I know it's very, very rough. Obviously, one of the issues that's key in post-acute COVID is to what degree it's related to COVID. And what you're looking at does seem to provide a way of addressing this. So what's your sense, what fraction of people whose symptom complexes might in isolation be seen as post-COVID really actually develop this post-COVID?
So that would require a step that we haven't done, which would basically be, can we incorporate, all COVID-19 patients and see if there is some, phenotype that we can establish based on the patients, for example, that have been tagged as UO 9.9, and then seeing if there are other patients that also fall in that same or, close to that area in whatever space we're operating in. And that's something at least I myself haven't done yet. I don't know if Justin, you've explored that yet.
No, not yet. I guess it's a short answer.
Great. Okay, well, let's see, Julie has a question, then we should move on. I think we also need to compare to more granular time periods in Sean's topic model clusters, which will probably be more similar to Hythem's ladder method. So, okay, so on to the monthly Recover Long COVID team project updates. Emily and Melissa. And thank you. Great, very, very interesting work.
Hey, everybody. So it's actually going to be me and Richard. Richard is playing the role of Melissa today. So we will be giving the Recover EHR update. Give me just 1 second to share slides. Can you all see that?
Yes.
Awesome. All right. Well, so this is I think we're doing these monthly updates on the progress of the Recover grant that we are delivering to the N3C community forum, because obviously many, and if not most of the things that we're doing in Recover certainly have direct implications for the work that you all are doing in N3C. So worth doing a catch up once a month. Just as a reminder, you've probably seen this slide before, but as Recover has particular focus areas that are shown here on this slide, and everything that we're doing as part of Recover is in service of one of these focus areas. So, you know, a huge goal is phenotyping PASC or long COVID to try to find which patients actually do have PASC and which do not. And then, as you just heard about in the great last presentation, we're trying to sub-phenotype folks that have long COVID into smaller categories that may be more specific to different types of long COVID than just saying that everybody has long COVID. It's important that we identify interventions that may work and risk factors that might make a given patient more at risk of getting long COVID or getting more severe long COVID. There is a significant community and patient engagement piece of Recover to ensure that we are involving patients who have long COVID at every step of the way. And then finally, this is more of a N3C specific piece of the project, but we are also working very closely with our contributing sites to enhance the N3C data to add some more stuff that we think will make our ability to do long COVID related analysis even more sophisticated. So we're going to update you on several of these things now. So here I am. For those of you who don't know me, I'm Emily Pfaff, and I'm at UNC Chapel Hill, and I lead the N3C data acquisition and phenotyping team. So data enhancement update. I'm going to give you a more specific update soon. I think for this particular crew, that means next month I will have a better update for you. The short story is that several of our sites have started submitting their enhancements, and we are deeply appreciative of that. And the enhancements that I'm talking about are admission, discharge, transfer transactions, so we can see who's been in the ICU, patient level social determinants of health. If sites have those, we certainly want to be able to take this into account for analysis. Data from ventilators for patients who were inpatient and on ventilators. We want to know the different parameters and settings if those are available. Dates of long COVID specialty clinic visits if sites have a long COVID specialty clinic, and then derived facts from natural language processing pipeline that Mayo is leading that will enable us to pull long COVID related facts out of unstructured text. So all of those are what we consider our data enhancements. And again, several sites have started submitting those, and it's been really gratifying to see those come in. However, the reason that I'm not giving you a more specific update on the status is that once we receive those data, we actually need to build new elements of our processing pipeline to accommodate those changes. And we are expecting those to be completed within 2 weeks. So the next time you hear from me, I am very hopeful that I'll be able to give you a more substantive update on that. The other thing to note is that Phenotype 4.0 was released, and this applies to all of N3C, not just Recover. So all sites were notified to update their phenotype code. And what the main difference between 4.0 and 3.0, which is what most folks are used to hearing about, is that 4.0 enables patients who do not have a COVID index to enter the cohort if they have a UO9.9, which is the ICD-10 for long COVID, or an M35.81, which is the ICD-10 for multi-inflammatory MISC, which is a pediatric condition very indicative of COVID infection. And of our 72 release sites, 26 of them have submitted under Phenotype 4.0, which is great progress. There was an NLP workshop, speaking of data enhancements, on April 15th that many sites attended, which was wonderful. And this was an opportunity for the sites that are participating in the NLP enhancement to talk to each other, to talk about potential validation strategies, as well as challenges and opportunities for multi-site NLP. For those of you who have attempted to do multi-site NLP in the past or have thought about that, it is incredibly challenging, and Recover and N3C has been an excellent opportunity to really take a test drive on this. it is, just because it's challenging doesn't mean it's not the right thing to do. It is the right thing to do, but it requires a lot of engagement from sites and a lot of collaboration in order to actually make it work. And so this workshop was a really wonderful opportunity to start some of that cross-site talking. This is just an example of some of the kinds of facts that we are extracting from the free text notes this is just sample data, but you could see that if a note said in it, or literally had the sentence, most pressing concern is fatigue, the OHNLP backbone, which again is being led by Mayo, that's their software, would identify the concept of fatigue, would be able to tag it with its appropriate concept ID, and then actually know whether that was a positive feature as opposed to a negated feature, like patient does not report fatigue, and knows the context in which that was expressed. So very useful data, and we all really look forward to actually using this data in analysis. Wanted to give an update on this. So you all saw this table last time I gave one of these updates. It's now been updated. So I'll just point to the things that are new. What you're looking at here is a summary of the different machine learning models that we have running right now in the enclave to identify patients who potentially have long COVID. We have two different models, one that's trained on patients who had visits to long COVID specialty clinics, and one that's trained on patients who have a U09.9 diagnosis code. The update on the long COVID clinic model is that it has been retrained on more data because, as I mentioned before, one of the data enhancements that folks are sending in are long COVID clinic visits. And so once we started getting those in, we actually had quite a bit more data than we did originally when we wrote the original manuscript to retrain the model. And I think performance didn't change much, but I think we did refine it a bit. And we have down here an estimate of the number of patients that the model is pretty confident are long COVID patients. And then the bigger update is that last time I talked to you, this model was not available, but it is now. So these are, this is a model that was trained on patients who have a U09.9 diagnosis. And note that if you are on the long COVID DUR, you can access the output from either of these models at the links on this slide. And then probably sometime in May, we are looking to release a combo model that incorporates the best features of both of these. And hopefully that will be the one model to rule them all. We're looking forward to that. And then I think I have two other updates. One is, again, another update that I think is not just impactful for Recover, but also for N3C as a whole, which is that many important COVID and long COVID research questions require us to know who is unvaccinated. And as I've told many researchers who work on N3C right now, we have to be very careful about saying that patients that don't have vaccine records in N3C are unvaccinated. Rather, the correct thing to call those folks are unknown vaccination status. They may have gotten a vaccine at a sort of mass vaccination site. They may have gone to a CVS. We may just not have a record of their vaccine. But that is a huge gap in our analysis because it is very important that we get better information on vaccination going forward. And we are working to do exactly that. So 3 steps that we are taking are working with sites to ensure that all available vaccine data is sent to N3C. So there are some sites that have vaccine data that may not have that incorporated in their current ETLs that end up going to N3C. And we want to make sure that where it is possible for sites to send those, that they are. We're also doing analyses to compare each site's vaccine coverage with the CDC's estimate of what the vaccination rate sort of approximately is in their area, so that we can get an idea of which sites have more and less complete vaccine information. And then I actually have coming this week, but it's actually available now. This is late breaking. If you go to the Enclave homepage right now and you scroll down to the bottom, you will see that we have visualized the vaccination coverage from each site labeled with a site ID so that you as a researcher can know which sites have higher amounts of vaccine coverage and which sites don't have any or have low. And that will enable you to pick and choose which sites you want to use in your analyses that involve vaccines. So we're really excited about that. And we're excited about all 3 of these things, actually. And I hope that by the next time I update you next month, we'll have even more specific information to share. And then finally, for my part, We have just submitted a manuscript on U09.9. Again, this is the newish ICD-10 code for long COVID that came into use October 1st of 2021, so relatively new. Myself and Reese Brown are co-first authors of this, and there are lots of folks who are part of the Recover group that are also involved and co-authors. And we did a bunch of analyses, including tracking uptake of this new code among our sites to see who's using it, who's not, as well as figuring out what are some common diagnoses, medications, and procedures that cluster around the time of U09.9 diagnosis, which we hope can help to better characterize long COVID patients, whether or not they have a U09.9 ultimately. So we submitted the preprint to medRxiv today. It should be available soon, and we'll circulate a link once that is available, and look forward to hearing back from reviewers on that. So I'm going to turn it over to Richard for some updates on analytics.
All right, thanks, Emily. Next slide. Okay, so we in the long COVID group have been exercising centralized control over our data flow. You can kind of see on the left from this monocle diagram, we start in with the concept steps and OMOP tables. And if you'll notice right in the middle, there is some data quality checks and a whitelist. So we're dropping some sites due to some automatic checks. And what this means for users outside of our group is that we have been identifying quality issues and periodically contacting the sites. These quality issues are flagged inside our project space, but the quality improvement overall should be filtering back to all of N3C. And we do have plans to templatize some of our data quality checks in line with some of the stuff that Hythem has discussed earlier as well. Next slide. Just an overview of some of the analytics we've done relatively recently, looking at the distribution of PASC or long COVID across our geographic footprint in N3C, starting with total number of patients with PASC on the bottom left. So you can see the density is up in the sites that we have more data, or the states that we have more data from, and then evolving to the middle figure, which is showing the relative frequency of PASC, which you can see we still have some heterogeneity issues to work out. This is actually a relatively old figure that we're going to refresh now that we have models trained on both long COVID clinics and U09 usage. And then finally, in the bottom right, we're looking at the relative incidence over time. So these are patients who have PASC and what fraction of them on the y-axis go on, or sorry, patients who have COVID and what fraction of them go on to meet our definition of having long COVID. Next slide, please. So currently we are waiting for further guidance from NIH and the Clinical Science Corps for which queries we're going to be asking in this, which is the second quarter of the first year of our grant. Currently, if I'm betting, it's probably analyzing the trajectory of deaths after COVID, also looking at pre-existing condition effects, but there are other queries which are on the table describing a deeper dive into some of the incidence of prevalence of PASC over time and geography, questions about vaccine effect, which Emily talked about, some of the issues we have to work through before we can do that analysis. And then there's starting to be a growing level of interest on long-term outcomes in some injury markers. So looking at eGFR long-term in kidney disease, for example, any sort of markers that we can measure long-term that may have been abnormal during acute COVID, which might be indicating a long-term injury. Next slide. So the last piece of data here is actually late-breaking analysis done from the PASC team, and this is work that's led primarily by Tel, Hemel, Johanna, and Elaine, and others in the risks subgroup. And so what we're seeing here is a consort diagram starting up at the top with all of our COVID patients, filtering down to those that are over 18 from sites that have diagnosis codes available for the UO 9.9 or sites that have the long COVID clinics data coming into us. Also making sure that we're excluding patients that died with their acute infection, and then making sure that the time frame meets our criteria. Next slide. So from this group of patients, we went and looked for controls so the cases are the patients with diagnosis of long COVID on the left, either from a long COVID clinic visit or the UO 9.9 diagnosis code. The controls get a little more complicated. There's 3 different control groups that the group is kicking around, including those patients that just don't have a long COVID or UO 9 hard visit, as well as a group of patients that not only don't have that, but are highly suspected of not having long COVID based on the machine learning classifier that Emily and others have developed earlier. So depending on which case and control group you look at, we can then match patients, in this case 1 to 5, with cases and controls, and then look at differences between those 2 populations. So next slide. So this is the preliminary results from that analysis. So these are all the different features that we looked at, trying to find effects of pre-existing conditions and demographics. So just briefly, middle-aged people more likely to have PASC, worse severity of stay, more likely to have PASC. You see a lot of pre-existing conditions that don't really have much signal. Female sex, more likely to have long COVID. We also see underrepresentation of Black and Asians. It's unclear whether this negative association is a mix of access or care-seeking behavior, and a lot of other stuff, like perhaps surprising is that there was no signal for diabetes in particular. So trying to wrap up here, one more slide. Next slide, please. So the last announcement we have is that the paper for unit harmonization is finally published. It is out as of this morning in AMIA, or in JAMIA. So this describes the full methods for where all of the harmonized data comes from in terms of converted continuous data from measurements in the enclave. And all right, it is 6 o'clock on the East Coast.
Well, thank you. Maybe we'll take it one or two questions. So congratulations. It's very exciting about the unit harmonization paper. It's quite a journey, but I
Thanks,
think
Joel.
really cool stuff. And that's very interesting what you're finding about long COVID. I thought that was actually very clever to define they really shouldn't have long COVID. We really don't think so as a group. What surprised you about what the correlations or lack of correlations?
So first of all, we saw this data merely hours ago. But in general, I think this is fairly confirmatory in a lot of things. There's some things on here, like some of the pre-existing conditions for some of the mental disorders seem to be protective. Hard to tell if that's a actual protective causal effect or some sort of association behind care seeking, or even a masking effect that changes how the model would view taking certain medications before or afterwards. So if you have the pre-existing condition and that condition is associated with PASC, then there's a little bit of a chicken and egg problem there.
One of the things that struck me is the non-effective diabetes, because as you know, we have a paper going out, or maybe it's gone out, I'm not quite sure the time case, which is a set of negative results involving diabetes and or COVID impact on long-term
Yeah,
Even-
severity of disease as well as weight gain is, I
Right.
think, the paper you're talking about.
Yeah.
Yeah. I don't really know. I think we have at least shown in the past that A1C levels affect your outcomes. So really more glycemic control is the salient variable rather than necessarily the diagnosis of diabetes. So it might be that if we included more fine grained measurement data here, that might help tease out some of that information.
Yeah.
It's also hard with models this large when you have so many comorbidities that you have a lot of collinearities.
Yeah, no, it's true. It's very hard. All right. Well, thanks. Really interesting session. Thanks to all the speakers, and we'll see you next week.
Mhm.